Okay, we're going to start 7.1. These are nth roots and radical exponents. Your essential question, how do you evaluate nth roots using both radical and rational exponent notation? So you guys are really used to square roots, and we're going to basically build off of that, and we're going to be able to take any root of any number. So what you need to know is if I have some base raised to some power, and that equals a, okay, then I can get b all by itself. I can solve for b by basically undoing what's happening here. So as we know, the opposite of, squaring something is to square root. Just like, and the opposite of raising any base to any power would be to take that same power as a root, okay? So it's going to look like this. B would equal then the nth root of a. Just like, for example, let's pretend that this is squared, right? So let's pretend this is 4 squared equals 16. Okay, so 4 squared equals 16. Then I would know that, well, if I take the square root of this, right, whatever this power is, take that root, then I would get 4 equals the square root of 16, which would be true. Maybe I have that written as an equation, x squared equals 16. Well, then I would know that, and this is a little bit different because there could be 2 things that could be squared to give you 16. I would know that x would equal positive or negative 4. So a lot of you guys get stuck on this, right? We know this is 4, okay, but when I have x here and I'm trying to figure out what x is, well, it could potentially be 2 different things, okay? So this right here, we call this radical notation. Okay, there's another way that I could write it though. Okay, I can also write it using rational exponents or rational exponent notation. Okay, so another way that this can be written, I'll just come down here, is to say that I could also say b would equal. Okay, now this is probably gonna be the first time you've ever seen this, but this is actually, we use it a lot. Okay, so let me just go up to here real quick. If I have b to the nth power, how can I get b by itself? What power could I raise it to get b by itself? And in fact, if I were to raise this to some power that I multiplied by n, and that became 1, then it would be all by itself. But I'd have to do it to both sides. So a way that I could do that is I could raise both sides to a fraction. If I raised it to like the 1 over n, right, then that n would cancel out or would reduce. Okay, so this could really be the same thing as saying that b equals a to the 1 over n power. Okay, that's a power. Okay, and we call this rational exponent notation. Okay, so there's 2 ways to do this, right? Both ways are equal. Okay, and put a little arrow there to show you that. So let me give you another example. Let's see. So for example, if 2 cubed equals 8, then I know that, well, 2 will equal, so again, to get rid of an exponent, we take the root, right? But we're going to take whatever root this power is. So I'm going to take the third root, or the cube root. So this is going to be the cube root of 8, which basically means what times itself 3 times will give you what's underneath the radical. Okay, so that's radical notation. Or another way I could write it would be looking at this and saying to myself, well, if I want to get 2 by itself, I can raise that to the 1/3 power because 3 over 1 times 1 over 3, well, that just becomes 1. And I'd have to do that to the other side as well, right? So this just becomes 8 to the 1/3. Okay, so radical notation, rational exponent notation. Rational means like a fraction, okay, and that's a fraction exponent. Sometimes you'll hear me say fractional exponent. It's probably not the correct vocabulary, but it makes a lot of sense, I think. All right, so let's do a couple more examples of these, and we'll do a formal example. So example 1, we're going to find the indicated nth roots. We'll do a couple of these. So the first one we'll do is if n is 3 and a equals negative 125. So what this is really saying is that I'm going to take a is my number that's underneath the radical, okay, and then 3 is the root that I'm taking, okay, so we're above and beyond square roots now. Now you can take any root you want. So I would rewrite this as the cube root of negative 125. Now you might say to yourself, oh my gosh, there's a negative under there. There must be an I. That's only going to be if this is even, right? Because you can take an odd amount, or you can raise any negative to an odd power, and it'll still be negative. Okay, so this is basically going to equal, you're just asking yourself, what times itself 3 times will give me negative 125? Well, that's going to be negative 5. Okay, and if you don't believe me, here I'll show you. This is since negative 5 cubed equals, negative 125. Okay, so that's why that works. So let's try another one. B. So our n, or our root that we want to take, is 4. And the number that we're going to take the 4th root of is 16. So the notation using radical notation is 4th root of 16. So what I'm asking myself is, what can I raise to the 4th root to get 16? So what number times itself 4 times will get you 16? Hopefully you realize that that's 2. So this here equals 2. So this is my answer. Okay, this is my answer. This is just me kind of proving it. All right. Let's see, is that one piece of paper? There it is. So let's talk more about rational exponents, because this is probably the first time you've had to deal with these. So we had learned in the past some properties of exponents. I think that was last chapter. And so you're going to apply all these properties that you've already learned to rational exponents and to exponents of any power, any type of power. Okay, so if I have a to the m over n, okay, that's a power there, but it's a rational power. I can rewrite this many different ways. I can rewrite this as, well, this is the same thing as a, maybe to the 1/nth raised to the m power. That's one way I could write it. Maybe instead you saw it as a to the m raised to the 1/nth, right? Because m over 1 would give me basically m over n when I multiply them, right? Any power raised to a power you multiply, in case if you forgot that. Or I could write this in radical notation, okay? So the way that you write this in radical notation is that whatever your denominator is, that's your root, okay? So that means that I'm going to take the nth root of a, and then I can look at this a couple of different ways, but I'm going to say I can take the nth root of a to the m, or I can take the nth root of a raised to the m. Either way, I'm going to get the same exact number. Okay, another property here was, what about our negative exponents? Okay, so remember what happens with negative exponents. It basically flips whatever the base is, right? So I could write this as, let's see, I could write it as 1 over a, then to the m over n. That would be one possibility. Okay, going back to this, I could write it as 1 over a to the m over n. Or I could write it as 1 over a raised to that, raised to that 1/nth power. Let's see, where did I do that? Over here. and then raised to the m. I could also write it in radical notation. I like to think a lot of times about these things in radical notation. So that's the nth root of a raised to the m, or the whole thing. So there's so many different ways you can go about doing this, and that's one of the biggest problems with exponents is when people ask for help, there's usually 3, 4, 5 different ways to approach a problem. So you might be sitting next to somebody working on a problem and they've approached it differently. It's not that it's wrong. It's that you guys need to see if you get to the same answer. Okay? All right, so let's do a couple of these. So example 2. We are going to simplify some rational exponent problems. So simplify. All right, so A is going to be 16 to the 5 halves. Okay, so, in my opinion, this is going to be way better if I can think about what root I need to take. And remember, whatever's in the denominator, that's the root that you're taking. Okay, so this is really the second root of 16 raised to the 5th power. So I need to figure out, what is the square root of 16? Well, hopefully you all know that. Okay, that's going to be 4. And then I'll raise that to the 5th power. Well, let's see here. 4 times 4 is 16, and 16 and 16 is that 256? And then one more of those. Let's see, 2. I did something wrong. What did I do wrong? 4, 0, 2. Carry the 2, that's 8, that's 10. 1024. Okay. Let's do another one of those. 64, let's throw a negative in there, to the negative 2/3. So, the first thing I'm going to do is I'm going to flip this. This is really 1 over 64. And you can write this a couple different ways, but I'm going to put this as to the 2/3 power. Because the 1 doesn't really matter. Yeah, there's a lot of things maybe I'll do another one where I show you guys that. $10.24. Okay, let's do another one. This time we'll use a negative exponent. All right, so if I have a negative exponent, I'm going to first take the reciprocal of whatever my base is. So my base here is 64, so this is really going to be 1 over 64 to the 2/3. Okay, and then I can think of that, well, this is really the cube root of 64 squared. So this is 1 over the cube root of 64, and then I'll square that when I'm done with it. Okay, so I end up with, so I have to figure out what times itself 3 times will give me 64. Okay, so what number cubed will give me 64? Well, I know that 8 times 8 gives me 64, so it can't be 8. Okay, it needs to be something smaller. And 5 is obviously not going to work. Okay, so and 6 probably it won't work. So I have to think about, what times itself would also give me an ending of 4 here 3 times. Okay, so it's going to be 4. 4 times 4 is 16 times another 4 is 64. All right, so this is going to be 1 over 4, and then I have to square that. So I really end up with 1 over 16. Okay, so what if I had, let's see. Let's just do one more of these. What if I had a fraction to start off with? So what if I had like 2/3? Oh, that's not good. Now I'm making up problems off the top of my head, and that never bodes well for anybody here. Let's try an easy one. So how about 25 over 64, the whole thing raised to the negative 1/2. Okay, so now I need to flip my base. So really it's going to be 64 over 25, and the whole thing is getting raised to the 1/2 power. So I could write it like this, which then tells me, okay, I need to take the square root of the top and the square root of the bottom. If you remember from last chapter, anytime you had a quotient raised to a power, that power was given to both of these. So really this answer is just going to be 8/5 or 1 3/5. Okay? So let's see, I'll go back and circle my answers. That way they're clear to you. And the last thing I'm going to do with you is solve some equations. So example 3, we are going to solve. All right, so the first one, you get 6x to the 4th equals 3,750. All right, and I want to solve this, which always means solve means get x by itself, okay? All right, so the first thing I want to do is get x alone as much as I possibly can. And, you know, when you're thinking about order of operations, when you're solving, you're usually kind of working backwards on order of operations. So I'll deal with that exponent very last thing I do. What I see now is that x is also being multiplied by 6. So that means I'm going to divide both sides by 6. So now I get x to the 4th equals, and that will be 625. Okay, so now I need to undo this 4th power. So just like when we had square roots, the way that I undid squaring was I square rooted both sides. So for this, you know, I like to think of it using those rational exponents. I'm going to raise both sides to the 1/4 power, which is the same thing as taking the 4th root of both sides, right? Because if I multiply these two together, I'm just going to get 1, and I'm left with x. And that leaves me with figuring out what times itself 4 times will give me 625. All right, well, I know that it's probably going to end in 5. And I know that 5 times 5 is 25. And 4 times of 5, or 4 5s, right? If I multiplied 5 4 times, I'd have a set of 25 and another set of 25. And hopefully this is one that you have memorized. 25 times 25 is 625. If not, it's up on the wall in my room, and I would definitely memorize that one. So x is going to be, now let's remember, if we're taking the 4th root of something, it's just like it's very similar to the square root. So I could potentially say all these are positive, which says 5, but could they all also be negative? What if they were all negative? Would that work out to give me a positive 625? In fact, it would. Okay, so this could be a positive or negative 5. Now, sometimes it's not going to work out that beautifully, and you're going to need to use your calculator. So let's do one where we have to use our calculator. And let's make it a little bit more challenging. How about, I got x plus 1 to the 3rd power equals 18. Okay, so, you know, if there was anything that I could undo that is right next to x, that would be awesome. The problem is I can't undo this because everything in these parentheses is getting cubed. So the first thing I'm going to do is basically uncube it. And when I say that, I mean raise it to the 1/3 power or cube root it. So if I raise it to the 1/3 power, I need to do both sides, which basically turns this into 1. So I'm left with x plus 1 equals, well, it's the cube root of 18. Now, do you know anything that can be multiplied by itself 3 times to get 18? Let's see. If it was 2, well, 2 cubed is 8. So let's do now 3 cubed. So 3 cubed, well, that's 3 times 3 times 3. That's 27. So there's nothing there. All right, well, this gives us a great opportunity to try and figure this out using our calculator. So, you know, again, you can think of it written like this or like this. When you're in your calculator, you're going to think of it using rational exponents, okay? So let's open up my calculator. Hopefully you have your calculator and it's working. So let's turn it on. Let's ignore that. Oops. Okay, so the way that you do this is using your caret, okay? You're not going to have, so you have like x squared here, but that's pretty much all you have. So you are going to use your caret, just like we do when we're using Desmos, or any of the, like I think Con also has you use it. Okay, so we're going to take 18. Again, I'm going to be thinking of it like this. Okay, take 18, I'm going to raise it, so I'm going to use that caret. Now, I'm going to raise it, and I'm going to put it in parentheses just to make sure that it knows that this whole thing is my power. 1 divided by 3. That's going to guarantee that it knows that you're raising it to the actual 1/3 power. All right, and then I'm going to press enter. And it's going to be approximately 2.62. So x is going to be approximately 2.62. Now, could it be, oh, and I'm not done. I'm sorry. I forgot about the plus 1. So x plus 1, and I'll just put an equal sign to make it easier on ourselves, and at the end we'll put approximately. So x plus 1 equals 2.62. And then from there, I need to get x by itself, so I'm going to subtract 1. X equals, that's going to give me 1.62. Okay, let's just go back to this part. So if I had put in a negative, okay, so, notice how I didn't do a positive or negative like I did here when I had that even root of 4. Okay, with odd roots, you're going to know whether it's supposed to be positive or negative. Because if you cube a positive, you get a positive. But if you cube a negative, you get a negative. So you would have to have a negative under here in order for your answer to be negative. Okay, so on odd roots, you're not going to end up with both positive and negative answers. On even roots, though, you will. Okay, so this is going to be my final solution. Oh, and I said I'd put approximately because it's not exact.